Okay, so on the subsequent page, I want to go through three mechanisms. And of course, on a multiple choice type exam, you're mostly going to be asked mechanisms in the context of reaction coordinate diagrams, or you may be asked to place intermediates in a certain order or to select an intermediate that does not belong. So the first reaction here is a hydroboration type, where we have an alkyl borane and THF solvent. So that THF is an aprotic solvent that does not appear in the product. And boron has a bond to hydrogen. It also has these two ambiguous carbon chains. Okay, so this is just like borane, BH3. But with alkynes that have two pi bonds, sometimes we use a dialkyl borane instead of BH3 to prevent it from reacting multiple times. So this is hydroboration. And boron, of course, only has three bonds. There's no lone pair, which means that the boron is sp2. And any sp2 atom has a p orbital, but because boron has no lone pair, it has an empty p orbital. Or boron is therefore the electrophile. So boron is going to be attacked by the alkyne, which is the nucleophile. However, at the same time, this boron hydrogen bond breaks and the hydrogen attacks back, or the hydrogen must be serving as the nucleophile in that back attack, donating electrons, taking them away from electrophilic boron. So I'm going to draw the transition state here. Okay, this is not a step or an intermediate, right? But the transition state is going to have dotted lines where one pi bond here is breaking, and we're forming new bonds to hydrogen and to boron at the same time. And the boron hydrogen bond is breaking. And the two R groups remain here on boron. Okay, so this is the transition state. Because the boron is the electrophile, it's partial positive. And the carbon of the alkene that is more stable with positive charge, or the alkyne, is the more substituted carbon. By default, the less substituted carbon has more electron density and more negative charge character. Okay. Any alkyne starts like that, where the less substituted carbon is more nucleophilic and the more substituted carbon is more electrophilic. But the hydrogen, because it's the nucleophile when it attacks back, it's partial negative. So this is the anti-Markovnikov transition state, where the hydrogen as the nucleophile actually adds to the more substituted carbon. Okay. So that leads to a product where there's two things you need to focus on about this product. First of all, the hydrogen's on the more substituted carbon, and boron is on the less substituted carbon. Or the regiochemistry of this is anti-Markovnikov. That's the only time we've seen anti-Markovnikov this semester is with boron. And it's because hydrogen, which is the nucleophile, adds to the more substituted secondary carbon. Okay. And then the stereochemistry is that the boron and the hydrogen are on the same side of the double bond, or they are syn, because this reaction is in what I call category C, or it's a concerted reaction, where we form the boron hydrogen the carbon hydrogen and carbon boron bonds at the same time. So since they add at the same instant, they have to add cis to one another, or on the same face of the alkyne. So you get that syn addition product. So it's a single concerted reaction with a single transition state and no intermediates. So this is reaction coordinate diagram B above. Many times you'll go on to take this and treat it with hydroxide and peroxide and make an enol. But if you're just given the alkyl borane, then you stop at that intermediate, the alkynyl borane. Okay, so for the next one, now we're treating this with water, which is a weak nucleophile, poor base, and room temperature. So this is going to be an SN1 E1 type process, and low temperature is going to favor substitution. This carbon, or the tertiary alpha carbon, can form a carbocation, and that happens first, no matter whether it's SN1 or E1. And recall that forming a carbocation takes energy input, or we're stealing the octet away from that carbon. So if the carbocation is an intermediate, then getting there is hard and slow to do. So that will be the rate limiting step, or the rate determining step. But now that we have a carbocation, it's very electrophilic, and therefore will go on to react very fast. We have two possible nucleophiles, water, and the other nucleophile is the alcohol, right? They're both weak nucleophiles. But what's faster is for an internal nucleophile to attack, as long as it forms a 5 or 6 membered ring. So this is an intramolecular SN1, where we're going to form a ring from nucleophile 1 and electrophile 5. Now this carbocation is sp2, which means it's planar. So it has an empty p orbital that can be attacked from the top. If it attacks from the top with oxygen, then the methyl gets pushed down. This stereocenter is fixed, and then we just fuse that 5-membered ring. The oxygen retains one lone pair and a positive charge. You could also attack with oxygen from underneath, which would push the methyl up. Once again, the oxygen retains a positive charge. Okay. So from here, the last step is simply to deprotonate, and you can use water or another alcohol in the solution. But the positively charged oxygen will be deprotonated. It's acidic because it wants a lone pair back. And that will generate 2 products. These products are diastereomers of one another. Okay, this chiral center here is fixed, did not undergo reaction. So that one has configuration, let's see, this is hard. 1, 2, S in both. And then the newly made chiral center is both R and S because we attacked from either the top or the bottom of that planar carbocation. So it's S in the bottom and R in the top. Okay, so here you get two diastereomers from this SN1 reaction. Because we had a fixed chiral center and we also had one chiral center that underwent racemization, or SN1. So this was 3 steps overall. Proton transfers are fast. Attacking a carbocation is fast, especially when it's intramolecular and forms a 5 or 6 membered ring. Here we made a 5 membered ring. The slow step is step 1, or getting to the carbocation. So this is reaction coordinate diagram C, where we have slow carbocation formation first. Okay. So then we have one more on this page where we add HBr to an alkene. And HBr, of course, is a strong acid. When that reacts with a pi system, it's going to give a carbocation intermediate. Okay, this is at high temperature or under thermodynamic control. This diene has 2 alkenes, right? One between carbons 1 and 2, and one between carbons 3 and 4. And they are conjugated. You have to determine where you should protonate first, right? When the hydrogen from HBr adds, that electrophile, or the hydrogen, will always add to carbon 1 or carbon 4. So if we protonate, either the 3,4 pi bond can remain intact. So if you protonate C1, then you get a tertiary allylic compound or carbocation. Okay. If you protonated C4, then you would get a secondary allylic carbocation. And we know that tertiary carbocations are more stable. So this one does not form as fast. Okay, being allylic means that this carbocation is stabilized through resonance, where I can push that pi bond up and show another resonance form. So when the bromide attacks, it could attack either that carbocation on the secondary carbon, or it could attack the tertiary carbocation. You get 2 products here. The 1,2 product is where we add the hydrogen to carbon 1 and the bromine to carbon 2. Okay. The 1,4 product is where we have the double bond migrate over and we added the hydrogen to carbon 1 and the bromine to carbon 4. These are both possible. Okay, let me show you the mechanism for step 1. It was this pi bond, which was more nucleophilic, breaking to attack the hydrogen, and the bromide serves as a leaving group. And we said that gave the tertiary allylic carbocation, which was stabilized by a secondary allylic resonance contributor. So the 1,2 product in these situations is always fastest because of proximity. It's fastest for H and Br to add across the same double bond. The thermodynamic product in this case is the 1,4 product. It can be either, it depends on the diene as to which one it is. But the thermo product is the most stable product. And the functional group we look at to analyze stability is the alkene. The alkene is more substituted in this 1,4 product. It's a tri-substituted alkene. So the major product you would draw under thermodynamic or high temperature is that more substituted double bond there. So this one was 2 steps where carbocation formation is slow, once again, and then attacking a carbocation is super fast. And so that is reaction coordinate diagram A, where there's no third step or proton transfer at the end.